Now that we've been working with radicals for a while, we're going to look at two specific examples of the ways these radicals can be used and the way radical equations can be used. The first example is something that you've probably seen before, and that is the Pythagorean Theorem. Now, Pythagorean Theorem says that if you have a right triangle, a right triangle, of course, would mean it possesses one right angle, that's a 90-degree angle, with legs A, B, and C, those are our lengths, then we know that if you take the length of the first leg and square it, take the length of the second leg and square it, add those values together, we'll get the length of the third side squared, which that third side, of course, is the hypotenuse. Now, this theorem also works in the other direction. In other words, if you had a triangle and you put the lengths into this formula and the formula gave you equality, then you could assume that you had a right triangle. So, given a right triangle, you know this theorem works, this equation works, and given this formula, you know that it's a right triangle. Now, the way we're mainly going to use it today is to solve for missing sides on a triangle. Now, given a right triangle, there's two things they could ask you for. They could ask you to find the hypotenuse or one of the two legs. Doesn't matter which leg you call A or which leg you call B. In the formula, it won't make any difference which one you name which way. So let's just go and work a couple of these examples. Let's say I have a leg of length 7, a leg of length 11, so we'll find the missing value, we'll find the x. In this theorem, this means that 7 squared plus 11 squared equals x squared. So let's go to the calculator. We see that 7 squared plus 11 squared is a 170. So we have that x squared equals 170. We've already learned that squaring and square rooting are the opposite of each other. So taking the square root of both sides, I can get an answer. So I'll hit second function and the square root button. What's nice about this calculator is I can hit second function and the negative sign, and it automatically knows that I want to use my last answer. And so x is a 13.04 when we round to 2 decimal places. So that's basically how it works when you're looking for a hypotenuse. Let's now look at an example of looking for a missing leg. Next triangle. Say this is a right triangle. And with a hypotenuse of 20, one leg is 15, other leg we'll call x. Again, putting it into the formula, we know that x squared plus 15 squared equals 20 squared. So doing a little bit of algebra before I go to the calculator, that means that x squared is equal to 20 squared minus 15 squared. So we'll see what that is. 20 squared minus 15 squared. It's going to be a 175. So that means that x squared equals 175. Same thing as before now. I'll take the square root of the 175. Of course, I could have inserted the answer here. And that is a 13.23 this time. So as you can see, a very easy formula to use. In any word problem where they describe a right triangle, you can use this procedure. For example, let's say we had a telephone pole that was 50 feet tall. You want to connect a guy wire to the top and have it reach the ground, and you want it to connect to the ground say, 6 feet from the base of the pole. The question would be, how long should the guy wire be? If we get to pick our own variable, we're going to want to use a c for the missing value. So we would say that 50 squared plus 6 squared equals c squared, where c is this side. So again, back to the calculator. 50 squared plus 6 squared is a 2536. So we've got c squared equals 2536. Again, back to the calculator, taking the square root of that answer gives me a 50.36. So c is 50.36. In other words, it needs to be 0.36 feet longer than the pole is tall, and it can connect. Now the next thing we want to work with, a different type of formula, is a distance formula. Let's say that we are graphing in the Cartesian plane. So here's our x-axis, and here's our y-axis. And we have 2 points. And we want to know what is the distance, the straight line distance between those 2 points. Well, if we sketch in an imaginary right triangle, hopefully we see that we can use the Pythagorean theorem to find this distance. We'll name this point x1, comma y1. This point we'll call x2, comma y2. Now, when you study slope, you learn how to find the lengths of these sides. The length of this bottom side, for example, is x2 minus x1. The length of this side, since it runs in the y direction, is y2 minus y1. Using the Pythagorean theorem again, we see that distance squared is equal to the x2 minus x1 square plus the y2 minus y1 square. Square rooting both sides, we find the distance formula to be square root of x2 minus x1 square plus y2 minus y1 squared. In case you're wondering, no, the square root can't cancel these squares because addition is going on at the same time, and that prevents that from happening. Now let's use the distance formula once. I'm going to show you the correct way to do it so that you don't have sign errors. And you're going to see that we can use this distance formula whether we draw the figure or not. Let's say that we have the points -3, 7, which of course would be back 3, up 7. That is a second quadrant ordered pair. And we have the ordered pair 5, -10, which is a fourth quadrant value. I'm going to put this into the distance formula. To find the distance between these 2 points, I'm going to put my parentheses in here, and we'll start putting in our values. x2, which is 5, minus x1, which is -3, and any negative number should go in parentheses. That's what goes here. y2, which is -10, minus y1, which is 7, goes there. Again, negative numbers in parentheses. If you need to, you can do this on your calculator in steps. 5 minus a -3. 5 subtract a -3 will give us an 8. -10 minus 7 will give us a -17. Now we have to square both of those. 8 squared is 64. The -17 squared we might need the calculator's help with. So hit squared, since that was our last answer, it'll square that answer and give us a 289. Now we add these two together. 289 plus the 64 gives us a 353. And finally, to take that square root of that last answer, which is 353, is at 18.79. So there's a quick, easy example of the distance formula in use. If you can remember the formula and get it written down correctly and not make any sign errors, it's a very easy formula to use.